Our seventh learning outcome for Unit 1 is that we can use a recursive equation, or sometimes we call that a recursive rule, to generate more terms in a sequence. And so for 7A, we are asked to find the next three terms in the sequence if f of 1 is 3, so that's our first term. And we're also given the recursive equation. So f of n equals f of n minus 1 plus 7. Sorry for the background noise. I'm at school right now and the announcements are on. So I'm going to use this equation, and this is the term that I'm starting with. So if I already know f of 1, the next term I need to find is f of 2. So that would be our second term. So n tells us like what term we're working with, and f of n is the actual value of the number in our sequence. Okay, so since I want f of 2, I'm just going to do my work over here. I'm going to plug a 2 in for n, so f of 2, and anywhere I see an n, I'm plugging in a 2. All right, so my recursive equation with the 2 plugged in is that f of 2 will equal f of 2 minus 1 plus 7. So I can simplify that. I know that 2 minus 1 is 1. So all that to say, f of 2 is f of 1 plus 7. So that's how the recursive equation or recursive rule works. I find my second term based on knowledge of my first term, and that's why n minus 1 is always one term less than n. So, okay, since f of 1 was 3, remember we're told that over here, 3 plus 7 equals 10. All right, so that's my second term in the sequence. So now when I want to find my third term, I'll do f of 3 equals, oops, I don't need a PC game, that's just coming up on my computer. F of 3 equals f of 3 minus 1, because I'm substituting 3 for n, plus 7. So again, that becomes f of 2 plus 7. So my previous term plus 7. Well, since I found that f of 2 is 10, this is now 10 plus 7, and we get 17. So that's how our recursive rule works. Now, I only found so far the next two numbers in my sequence, that f of 2 is 10 and that f of 3 is 17. But I might notice, looking at my recursive rule, if I interpret this as add 7 to the previous term, I can also just write out the sequence without evaluating the function. So the work that I just did over here, I evaluated that recursive equation that was in function notation, but I could also just interpret the pattern from my equation. And for some students, you might prefer one way of thinking over the other. So if I write out the first several terms of my sequence, the sequence begins at 3, we were given that, then it goes up to 10, then 17, and since I know my sequence is increasing by 7, I know it's arithmetic, I could just keep adding 7s. So 17 plus 7 is hopefully 24. 24 plus 7 would be what, 31? Yeah, so as I keep working up, I just could keep adding 7. So it said find the next 3 terms. I actually found the next 4 terms, but that's okay. We could keep going if we needed to. All right, so similarly, 7b, I've got another recursive equation, but this time I see multiplication. So I could interpret this as my next term, or the term I'm looking for, so f of n, is my previous term times 5. So if you are comfortable reading that, you don't have to evaluate f of n, but just to illustrate that one more time, I'm going to. So if I already know f of 1, and I want to find f of 2, I'm going to substitute 2 for n. So f of 2 is f of 2 minus 1 times 5. And since 2 minus 1 is 1, this becomes f of 1, which is negative 1, times 5. So I get negative 5. So again, I can use that function notation. I can plug in the values of, I can plug in for n, the place in my sequence. Like if I want my second term, I plug in 2. If I want my 10th term, I could plug in 10, but then I would have to know f of 9 to get there. Okay, so if I write out my equation, or my sequence, I know my first term is -1. Then I got -5. And I can see that I'm always multiplying my previous term times 5. So that's going to become -25. My brain just took a moment there. And then our next term would be -125. And you're welcome to use a calculator there. Hopefully I didn't just make any math mistakes. I sometimes do. All right. If we look at our next learning outcome, number 8, it says I can determine the common ratio of a sequence when I know the sequence is increasing or decreasing by a percent and use it to write an explicit equation. So just a quick, I know we haven't spent a lot of time on this in class. We did in our 6th lesson, Home on the Range. This is, if you're struggling with this, that is where we kind of did that learning. I think we have a way to go to formalize it. But just a quick reminder, anytime I'm operating with a percent or a percentage, I have to be able to write it as a decimal. So for example, if I have 20%, percent means per 100. The word cent or cent, if you speak French, means 100 in a lot of languages. So, and we could think 1 cent in American currency is 1/100th of a dollar. So all that to say, 20% is the same as 20 divided by 100. And as a decimal, that's going to be 0.2 or 0.20, if that kind of helps you see the 20. But that is 20/100ths. So remember, in our place value system, the 2, we call that the 10ths place, and the 0 would be in the 100ths place. So I could either interpret that as like 2/10, if I simplify that fraction, which is the same as 1/5, or I could think of that as 20/100ths. All right, so more generally speaking, if you have a percent, like 53%, you could move the decimal, like 53, the whole number, move the decimal to the left twice, and that is effectively the same as dividing by 100 because of our base 10 place value system. Okay, or number system. So in example 8, Ariel's used car is worth $12,000. So I'm going to think about that as how much her car is worth right now. Her car decreases in value by 10% each year. So like at the beginning of this example, or at the beginning of our knowledge about Ariel's car, we know that it's $12,000, but after 1 year, her car will be worth 10% less than what it is currently worth. So we're trying to find the common ratio and explicit equation that could represent this situation. So let's start with the ratio piece first. So if I find 10% of 12,000, 10% of 12,000 is the same as, I could think about dividing 12,000 by 10, or I could multiply it by 0.10, but when I do that, or 0.1, 0.1 would be the same as 0.10, 10/100ths. When I do that, I just get 1,200. So that's not what her car is worth after 1 year. That's how much her car is losing in value after the first year. And it won't be a constant change. Like her car won't decrease in value by $1,200 each year, because the next year she's going to lose 10% of what it was worth then. So like that number is going to change. This will be a geometric pattern that we see. So all that to say, 10% or 0.1 is not the common ratio, because what we need is the number that we can multiply by to find the value of her car currently, or rather after 1 year. So if her car decreases in value by 10%, what I would think about is how much value does it retain? Like how much value does it still have if it decreases by 10%? So that's going to be 90%. So how do we get that? Well, 100% minus 10% is 90%. So if you lose 10% of something, you still have 90% of that thing left. So we do need to think about this as decimals. So we should get 0.9. All that to say, 0.9 is our common ratio. And so we could generalize that when we have percent decrease, and we're going to talk about this more this year and in Algebra 2, but when something is decreasing by a percent, to find the ratio, I need to subtract my percent decrease. So 10% was the percent decrease, right? Percent dec, that dec stands for decrease. We subtract that number from 100. So our common ratio is 0.9 or 90, if that helps. All right, so then we're asked to write an explicit equation. Well, we could do this, since this is going to be geometric, we know that our equation, if it doesn't matter to me if we use function notation or y and x, but I know that my equation will kind of be in this form where I have some starting value out here. I'm multiplying by my common ratio or my growth factor, and the variable tells me how many times that multiplication happens. So if her car starts at the beginning as being worth $12,000, that is going to be my starting value, $12,000. The growth factor we said is going, or the common ratio, growth factor is another term we use when we're talking about exponential growth. So the common ratio is 0.9, and then if I'm using x and y, I could just have to the power of x. Sometimes we'll use t to represent time, for example. All right, so this is the equation that we're looking for. Now, if it helps, when we did this in class, we made a table. So if it helps, after, we could say at the beginning, when no time had passed, her car was worth $12,000. If I multiply $12,000 by 0.9 after 1 year, that's how much money I will have, or that's how much her car will be worth. So I could think of this next value in my table as being $12,000 times 0.9, 9/10. And so whatever that number is, and I'm not even calculating it, you can do that multiplication, but the next year, whatever that value is gets multiplied by 0.9 again. And so when I see the two multiplications, I'm multiplying by 0.9, that's the same as saying $12,000 times 0.9 squared. So if we continue this pattern, for any x, my y value is going to be $12,000 times 0.9, and then it's how many 0.9s do we multiply by? Well, this is that pattern we're seeing in the table, that the thing that varies is going to be the same as our variable x here. So that's why we can represent that with just an x. So that's the kind of thinking that helps us get to our explicit equation. But I know this is hard, and we haven't practiced this specific topic a lot yet. All right, one more kind of similar question. Sebastian wrote a sequence. The first term of the sequence is 10, and each term in the sequence increases by 30%. Find the common ratio and explicit equation that could represent this situation. So, excuse me. All right, so if the first term of my sequence is 10, if I wanted to make a little table, and you don't have to, but I like to make tables, they help me. N would be 1 if my first term is 10. And then we're told each term increases by 30%. So again, 30% as a decimal is going to be 0.3 Again, we just divide 30 by 100, 0.3. But if I multiply 10 by 0.3, I'm going to get the number 3. So I know that my next number in the sequence can't be 3 because I'm told the sequence is increasing by 30%. But since 3 is 30% of 10, that means my next term is 10 plus 3. So if I look at that number, and I know that number is 13, right? That 10, oops, I don't know why that didn't change color. That 10 is 100% of this first 10 that I started with, and then I'm adding to that 30% of this 10 that I started with. So that kind of gives us a clue about how to find our common ratio. So anytime I have percent increase, percent growth, I'm going to add the percent by which I am growing to 100, and that gives me the number that I'll need to use for my common ratio. So if the next term is 30% more than my previous term, that's 130% of the previous term. So I could write this as 1.00 plus 0.3 equals 1.30. And I know I don't need that 0 at the end. Sometimes it's just nice when we're working with percents to see it there. So 130% is 1.3. So that's my common ratio. And this is something we'll talk about more this year, and certainly in Algebra 2. But so we said percent decrease, we subtract from 100. Percent increase, we add to 100. So I'm going to add the percent by which I'm increasing to 100 to get my common ratio every time. All right, so then lastly, we're asked to find an explicit equation that could represent the sequence. Well, this time, it's not quite as easy as the one before, because I know that my value of f when n is 0 is not 10. 10 is the value of f when n is 1. So a couple of ways we can think about this. One way is that I could just continue, like I could think about my table, that the next, like I'm going to kind of rewrite this differently. So the number I get here, we said, is the number 10 times 1.3. And that's going to be, what, 13? So I'm multiplying 10 by 1.3 one time. So this next number, it is going to be 13 times 1.3, but that's the same as 10 times 1.3 times 1.3. So this part being our previous term, but I'm multiplying by 1.3 again. So I could think of that as 10 times 1.3 to the second power. To get to my fourth term, I'm going to take that last number, which I could represent as 10 times 1.3 times 1.3, like that was my previous term, and I multiply by 1.3 again. And I could write that as 10 times 1.3, excuse me, to the third power. So if I can get to this condensed form, what I notice is that the only thing that's changing or varying is the exponent. And if this pattern were to, like, if I work this pattern backwards, this first number would be 10 times 1.3 to the power of 0, which it is, because 1.3 to the power of 0 is 1. So if I compare the thing that is varying to my independent variable, and I try to relate those, what I notice is that the number that I'm plugging in for my exponent excuse me, I'm still sick. The number I'm plugging in for my exponent is always the value of n minus 1. So to generalize this, if I plug in n, so if I find my nth term, what I would do is I would take 10 and I would multiply by 1.3 n minus 1 times. So if n is 100, I'm going to take 10 and multiply by 1.3 99 times. Okay, so that's one way. That's how we can get to our explicit equation here. I'm going to write it over here in orange, that it is indeed f of n is 10 times 1.3 to the power of n minus 1. So that should generate any term in our sequence. But there's one other way that we've seen this in class, and it doesn't always make sense in the context of the problem. But what if I found n, or f of n rather, when n is 0? I'm going to just erase this to make another spot in my table here. So what if I go back and add a spot for n to be 0, which in a sequence doesn't make sense. We don't start counting with 0. 0 is not what we call a counting number. If I, am picking up markers from my desk and counting them, the first one is 1, not 0. But all that to say, if I work backwards, so going down my table as n increases by 1, I'm multiplying by 1.3. But what if I work backwards and divide by 1.3? So I'm doing this off screen because I don't have my little calculator loaded while I'm filming this for this video. But on my phone calculator, I'm doing 10 divided by 1.3. Ooh, and I get an icky number. Ooh, I really don't like that number. It's yuck. It's like 7.692 and some change. What I could do to express that, if I don't want to get such a yucky number, yucky is definitely a math term, y'all, I could just write f of n here as 10 divided by 1.3. Ooh, I don't love that there's a decimal in my denominator, but what if I multiply that whole fraction? Let me do this where we can actually see it. If I have 10 divided by 1.3, I could multiply both the top and bottom of that fraction by 10 just to get rid of having that decimal in my denominator, and I get 100 over 13. So if you did 10 divided by 1.3 in your calculator, you could get 100 divided by 13. You should get the same number. That's how I'm going to just describe this number, as 100 over 13. Because otherwise, we just get a weird decimal 7 point something. I mean, you could use that. We would just have to round. So another way we could write our equation, although for this one it's hard just because that's such a weird number, is I could write it as f of n equals, I'm going to call this 100 over 13 instead of using 7.69230769 times 1.3 to the power of n. So we've talked about this in past explicit equations, but essentially when I'm starting with my value of f when n is 0, I just have an n here. When my starting value instead is the value of f when n equals 1, that's when I see n minus 1. And just to drive this point home for anyone who's watching this video, let's pretend that I started my equation. Let's say that I started with when n is 2. Like, let's say I used this value, the 13, in my table. I could write an explicit equation where my starting value is the value of f when n is 2. I would have the same growth rate, but my variable expression in my exponent would be n minus 2. So that's not a coincidence. If this is my second term, I have an n minus 2 up here. So that's a pattern we've been slowly developing and observing as we work through these in class.